Welcome back. This is the fourth lecture of this week and we continue with mutation testing. In the last couple of lectures, I'd introduced you to the topic. We discussed a reasonably exhaustive list of mutation operators in the last lecture, and they were applied at the unit level. Before we move on to interface level mutation operators, it helps to understand how mutation testing compares to the techniques that we saw earlier. In the beginning of this course, we saw graph-based testing. Later, we saw logic-based testing. They had slightly different flavors. They could be applied for source code, for call interfaces, graph-based testing specifically. Logic-based testing was focused on testing the logical predicates that come in decision statements. Mutation testing, I said, is more like debugging technique. It applied by making a change to a program and then testing whether that change, what effect does it have on the program. It so happens that you can still compare mutation testing with graph and logic-based testing, even though then by nature they seem to be very different. So the idea of this lecture is to help you understand how mutation testing compares with graphs and logic-based testing. In the next one, we'll continue with mutation testing at the level of interfaces. So in terms of a testing criterion, mutation testing is very good in finding errors. That's mainly because in software testing, Pareto principle applies. 80% of the errors are supposed to be focused on code. And mutation testing is a good debugging technique for finding errors that occur in coding, small errors that occur because of mistakes in coding. The nice thing is mutation testing, even though its flavor seems to be different from graph-based testing and logic-based testing, you can recreate the same effect that you have on a specific criteria of graph or logic-based testing by using mutation testing. So we can pick and choose mutation operators from the list that we saw to impose requirements that look similar to certain graph-based testing coverage criteria and certain logic testing coverage criteria. And suppose we take node coverage in graph-based testing that intuitively says visit every node in the graph. That's the test requirement. And as far as applying it to source code is concerned, it means execute every statement in the source code. This is the test requirement. It is met by a set of test cases that walk through paths in control flow graphs that end up visiting every node or executing every statement. The same effect of reaching or executing every statement can be recreated in mutation testing by using a custom set of mutation operators. So this is why we say those set of mutation operators are set to yield node coverage as a criteria. So mutation operators in general, if a set of mutation operators are used in a specific way to achieve the effect of certain other kinds of coverage criteria, then we say mutation operator yields those kinds of coverage criteria. So we will see what those kinds of specific subsumption are. Another important thing is coverage criteria typically impose a specific or a local requirement on the software artifact being tested. If I say node coverage, I apply it at a method, it means execute every node or every basic block that corresponds to the node in the code. If I say edge coverage, it means execute every branch in the control flow graph. Mutation testing, on the other hand, especially strongly killing mutation testing, says mutate a program and ensure that you write a test case such that the output of the original program ground string is different from the output of the mutant. So its flavor is different. It seems to impose a stronger global requirement. So what we do when we compare mutation testing to other kinds of coverage criteria is to consider weak mutation testing. By weak mutation testing, what we mean is changes that are specific to a local statement on which is being mutated. And strong mutation testing insists that output is different. Weak mutation testing says that at the statement that you mutate, if you look at the state of the program, The state of the ground string would be different from the state of the mutant. That is enough for us to compare mutation testing with certain graph and logic-based coverage criteria. The first graph-based coverage criteria that we would like to compare mutation testing is that of node coverage. It's fairly easy to see that mutation testing subsumes node coverage. The way we do it is node coverage insists that you visit every node, you visit every statement in the program, or you visit every node in the control flow graph. A way to achieve the same effect, to make the same test requirement as node coverage, is to replace the statements that you want to visit by appropriate BOM statements. So with that statement, and write test cases to kill that. So by writing a test case to kill a mutant that is produced by replacing a particular statement with a BOM statement, you're ensuring that you're reaching that particular statement. Now repeat the same thing for the next node or the next statement that you want to reach. So in effect, by creating several mutants which take turns to replace specific statements with BOM statements, we can recreate the effect of node coverage using mutation testing. It is in this sense that mutation testing subsumes node coverage. Mutation testing also subsumes edge coverage. What is edge coverage? There was a predicate labeling a decision statement, and two different edges go out of that particular node in the graph, in the control flow graph. One takes the true branch, one corresponds to the false branch. We saw mutation operators that let us replace logical predicates with true Boolean constant and with false Boolean constant. So a mutation testing can be made to subsume edge coverage by replacing it with true and replacing it with false. This forces each branch in the program to be executed. So in effect, mutation testing subsumes edge coverage also. The same thing, edge coverage in graphs is the same as predicate coverage in logic. We all know that. Because edge coverage says execute true branch and execute false branch that come out of a particular node. And that's exactly what the predicate coverage does also, because it makes the underlying predicate corresponding to the decision go true ones, go false ones. So it's in the same spirit that mutation testing subsumes predicate coverage. In fact, mutation testing can be made to subsume clause coverage also. A predicate can be composed of one or more clauses, if you remember logic coverage criteria. To make mutation testing subsume clause coverage, take each clause and replace the entire clause once with a Boolean constant true and once with a Boolean constant false. This will end up having the same effect as making the clause become true once, testing it, and making the clause become false once and testing it. So mutation testing subsumes predicate coverage and clause coverage in logic-based testing, and it also subsumes node and edge coverage in graph-based testing. Now you can ask, does mutation testing subsumes all combinations coverage in logic-based testing? The answer is an easy no, because if you see all combinations coverage tests for all possible values of true-false values of the various clauses, the entire truth table. That clearly cannot be mimicked by one or more mutation operators to produce so many different mutants, or much more than 2 power n mutants. We don't know how to do it. What about the other coverage criteria? Yeah, so this explains the clause coverage part. These slides explain, which I briefly explained to you, right? So a predicate is composed of one or more clauses, and these clauses are combined using logical operators. So you can use mutation testing to kill the clauses. So maybe I'll let these slides be as a part of the lectures and skip over them and move on to the next part. Mutation testing also subsumes active clause coverage, specifically general active clause coverage. If you remember what active clause coverage was, it says take each clause to be the major clause, make the major clause once true and once false, and see whether it influences or determines the predicate. And general active clause coverage doesn't put any restrictions on the values of the minor clauses. So it requires each clause and a predicate to evaluate to true once and determine the predicate, and each clause in the predicate to evaluate false ones and determine the predicate. So you create mutants of the predicate by taking the clause that you want to influence, the major clause, substitute it with true, and take the predicate and substitute it with false. This delta PA true represents in the predicate P, take the clause A, substitute it with true. Similarly, delta PA replaced with false says in the predicate P, take the clause A and substitute it with false. So for killing this, you need to have a different value when A is substituted with true than in the original predicate. This is exactly what general active clause coverage criteria by definition is. So mutation testing subsumes GACC. Mutation testing cannot be, it doesn't make sense for mutation testing to be compared to correlated active clause coverage or restricted active clause coverage, because like combinatorial coverage, they look for pairs of clauses. It says minor clauses in CACC. It says minor clauses take values such that the major clause determines the predicate. So this is not possible to recreate this effect by using one or more mutation operators. Similarly, RACC says minor clauses all take the same values when the major clause is becoming true or false. Again, using one or more mutation operators, it's not possible to recreate the effect of RACC. So we don't know whether mutation testing subsumes active clause coverage. Same thing, we don't know whether mutation testing subsumes inactive clause coverage. It's more like it doesn't make sense to strive to get mutation testing to subsume or not to subsume, because by nature their flavors don't match. Mutation testing, now coming back to graph coverage criteria, mutation testing subsumes one of the data flow coverage criteria, namely all definitions coverage. If you remember, we'd seen 3 data flow coverage criteria. Take the control flow graph, generate data flow graph by augmenting the nodes and edges with definitions and uses of variables. And then you have 3 different kinds of data flow coverage criteria. One that covers all definitions, one that covers all uses, one that covers all DU paths. Mutation testing subsumes all defs coverage. Just for this part, we need strong mutation. Why so? Because you see, all definitions says write test cases that execute or cover every variable definition at least once, right? So we restrict ourselves, our focus to statements that contain variable definitions. And what we do is to simply delete those statements. In general, we don't delete individual statements in mutation testing, but for the sake of argument, for the sake of showing how mutation testing can be made to subsume all definitions coverage, what we do is we could take the statements that we have for definitions, variable definitions, and delete the statements, and this implicitly has the same effect as that of covering the statements that define the variables. Yeah, so consider a statement SI. Let's say that contains a variable X, and MI is the mutant that deletes SI. So there is a statement SI in the ground string that defines a variable X, and I just delete that statement SI. I get a mutant, let's call it MI. Now to strongly kill the mutant MI, I must write a test case that causes the removed statement to be reached, lead to an incorrect state after executing the removed statement, and result in an incorrect output. Now, if you see, in the mutant, the statement SI is deleted. So the value that was assigned for X by the statement SI will not be assigned. So this will result in an incorrect state. And I can always let it propagate to the output, because if X is itself an output variable, then right there I have infection. If X is not an output variable, not defining X at S typically results in an incorrect output, and this will happen if X is irrespective of whether X is defined or not defined at a later stage. So what did we see? We saw some of the graph and logic coverage criteria and understood how a tool like mutation testing can be used to recreate the same effect that was assumed by graph and logical coverage criteria. It's in this sense that we say mutation testing subsumes those specific coverage criteria. So we saw how mutation testing subsumes node coverage, edge coverage, and all definitions coverage amongst the various graph coverage criteria that we saw. We also argued just now how mutation testing subsumes predicate coverage, clause coverage, and general active clause coverage. We cannot argue, and it doesn't make sense to say mutation testing subsumes other logical coverage criteria. Similarly for the other graph coverage criteria. So we don't consider them as being subsuming the other. So that was a very brief on mutation testing subsuming other kind of coverage criteria, just to give you a flavor of how to think of one kind of testing in terms of the other kind of testing. In the next lecture, we'll get back to purely mutation testing and see what are the kind of mutation operators that are applied at call interfaces for design integration testing by mutating the call interfaces. I'll stop here for now. Thank you.